Hi, my name is Miloš and welcome to Element 14 Presents. Today we're gonna go for a run, but before we do that, we're gonna measure some heart signals, we're gonna make our own chest strap for recording our pulse, and we're gonna analyze all of the data and write our own custom algorithm for detecting that pulse. Let's get right to it. The focus of today's videos will be fitness trackers. Most people have some kind of a smartwatch, and all smartwatches, or most of them, have a PPG sensor on the back. This is the blinking green and red light that you can see on my smartwatch here. And while they work pretty good, I've noticed, and you can see a lot of comments online, that sometimes they're not that accurate for tracking pulse. Another popular options are chest straps. So this is a chest strap, and this here is a sensor that directly measures your heart signals. So for this video, my idea is to show you how we can actually make our own chest strap sensor that connects to your phone just like a commercial device, and we're gonna write our own algorithm for detecting your pulse and sending that data over to Strava for recording your runs. Let's first draw how this is all going to work. Let's take a look at what we will be making in this video actually. First of all, let's see where this sensor goes. So the strap with the sensor goes underneath the pectoral muscles, and here you can see where the electrodes are. We will have another electrode, but the placement of these two is important for actually measuring those heart signals. So what do we need inside? First, we need an analog front end. This is used for signal conditioning, since those ECG signals that we're trying to measure are really small voltages, so we need to amplify them. We need to filter out some noise. Besides that, we need an MCU that will read that ECG signal from the analog front end. It needs to run some kind of algorithm to calculate the heart rate from that signal, and in the end it needs to send that heart rate data to a phone over BLE, and I'll show you how to do that so that our device can function just like any other off-the-shelf device. Besides that, we just need a battery and some power electronics to power everything, and I will just use a small repurposed one-cell lithium-ion battery. Besides that, I will be wearing a smartwatch on my wrist, so we can compare the data from my smartwatch to the device that we're gonna make in this video. In this way, we will have a pretty easy way to see if our device is working as intended. The smartwatch measures our heart rate using a PPG sensor. Before that test, let's record some ECG data and see how that looks like and how we can implement an algorithm to detect our heart rate based on that signal. My initial plan for this video was designing a custom PCB featuring the ESP32 IC in the 2-wire mode, because all chest straps usually use just 2 electrodes, but somehow I got it wrong. I tried following the datasheet, I tried resoldering it many times, it just didn't work. This doesn't mean I quit. I will redesign it with a new chip and new MCU, but because I really wanted to test it out and test out the algorithms, I decided on making a much more DIY friendly version using the all popular ESP32 ECG module that you can pretty much get anywhere. So let's see how the signal looks like when we connect electrodes to this module, and also let's take a look at the algorithms that are used for detecting the heart rate when we have that signal. To record the ECG signal, what I did was write this short script for the ESP. So what it does, we can define where our module is connected, how many samples we want, and the sample rate. So I went with 200 Hz sample rate, and I want 20,000 samples, which comes about to 100 seconds. So besides that, this just uses the ESP timer, so it will sample it 200 times a second, and once it samples all of those samples across 100 seconds, it will print them out in an array that I copy to a notepad, and after that I copy it to Google Colaboratory. I'll load it here as data, and then if we print it out, this is what we can see. This is the whole data set, and if we take a look at just a small segment of it, we can see that the data actually looks really nice. We can see that the whole QRS complex. So the signal is really good, and we can continue working on the algorithm now. You've seen how the ECG signal should look like when we connect our module, so that you know if you decide to recreate your project, to know how that signal looks like. I need to warn you, I'm using an opto-isolator, so please be safe. You are connecting electrodes to your body, so do that in your own risk. Now that we have that signal, we need to detect the R peaks in real time. How do we do that? We need some kind of an algorithm, and I'm now gonna show you one of the most famous algorithms. It's from a paper published in 1985, and it's called the Pan-Tompkins algorithm. So first of all, let's see how the logic behind it, how it all works. Then we're gonna program it in Python, and then we're gonna transfer that code to our MCU so we can run it in real time and detect our pulse and send it to our phone. In this drawing, I'll try to explain shortly how the Pan-Tompkins algorithm works. The first part is pretty straightforward. We need to get a raw ECG signal and pass it through a few filters. We first pass the signal through a bandpass filter, which we will implement as a low pass followed by a high pass filter. We follow up with a derivative filter, then by squaring all samples of that signal, and finally by applying a moving window integration. On that signal, we perform peak detection and end up with something I will call int peaks. We also perform peak detection on the filtered signal right after the bandpass filter, and I will call that field peaks. To understand the rest of the algorithm, we need to define a few parameters first. Peak is the value of the peak that we have detected, SPK is the running estimate of the signal peak, NPK is the running estimate of the noise peak, and we have TH1 and TH2, which are thresholds 1 and 2. Threshold 2 is usually calculated as 0.5 times threshold 1. We need these parameters for both the int and field peaks, so I will use I and f suffixes for these values. I will now draw what an ECG signal looks like and how it looks after our moving window integration. Don't forget, we also ran the peak detection algorithm on both, and this is how you can expect these detected peaks to look. Some will be there where you expect them and want them, while there will be a few that appear because of noise. Now we come to the more complex part of the algorithm. I will cover just the basic principle here. For full details, I highly suggest looking at the actual paper, which will be linked on the E14 community and is free to view for anyone. We begin by iterating through the int peaks. All of the parameters that I've written above are first initialized and then recalculated at each new peak, as you will see in the code. But for now, so I can explain it more easily, just imagine the thresholds 1 and 2 looking like this. Remember, threshold 2 is 0.5 times threshold 1. Let's call this peak A, and we just check whether peak A is above the TH1E value, and if it is, we now need to check whether there is a field peak that satisfies these conditions. 1. The value of that peak needs to be greater than the TH1F value, and 2. The timing of that peak needs to be within a certain time range, for example 150 milliseconds. Time-wise, these two signals will be shifted a bit because of all of the filters, so naturally the peaks won't line up ideally either. Since we found a matching peak in the field peaks, we can classify it as an R peak. If we didn't, we would just mark this as a noise peak. Either way, based on the type of the peak, we update our SPK, NPK and thresholds. I'll show you how to do that in the code. As we detect and classify new R peaks, we need to keep track of RR intervals, but we will do that in RR1 and RR2. We keep 8 values in both arrays, but for RR2, we add an RR value only if the RR value we want to add is between 92% and 116% of the average value of the RR2. Another thing we need to keep a lookout for is that if a peak we are analyzing time-wise is more than 166% of the RR2 average from the last detected R peak, this means that the peak should have been detected by now, and we need to implement the search back algorithm that goes back and starts from the previously detected R peak and uses the smaller threshold 2 to find a new R peak. After that, we get back to this peak. We also need to make sure that R peaks aren't within 200 milliseconds of one another. There are a lot of small details here. Let's go take a look at the code and how this algorithm looks in practice. And we're back in Google Collaboratory. Here is our ECG signal. So let's get to implementing the Pan-Tompkins algorithm. As you've seen, there's quite a bit to do. So first of all, the bandpass filter that we'll implement as the low pass and high pass filter. Here is my implementation of the low pass filter, and if you take a look at how the paper implemented it, I did exactly the same thing because my goal with this was to stay true to the paper and not rely on any libraries, so we can more easily transfer this code to the Arduino. When we plot this graph out, here is how this signal looks like, and this is just a random segment of the ECG signal, so we can just have some kind of representation as we go step by step. After the low pass filter, to complete the band pass filter, we need the high pass one. As you can see, the implementation is again the same as in the paper, as is shown on your right, and here is that signal. After that, same thing with the derivative filter. This is the signal after that. After that, we're just doing some squaring of every one of the samples from the filtered signal. After that, we have the moving window integration, and I've put the window size to 30 as Dave also did in the paper. So this signal now probably reminds you of the signal that I've drawn in the drawing. And now we need to detect the peaks on this signal. I've written just a simple peak detection algorithm that uses a double-sided window and just finds the maximum value there. And this is the result of it. By adjusting this window size, how sensitive this filter is. And as you can see, we have detected what are the R peaks. You can see them here. We've also detected the T waves, and there are some other peaks like this one here. But that's what Pan-Tompkins algorithm is supposed to actually categorize, to figure out which are the R peaks and which are just noise. But to do that, we also need to run the peak detection algorithm on our filtered signal, and this is how that looks like. Now we get to the actual algorithm itself, where we're just gonna work with the integral peaks and the filtered peaks, as I've called them. So again, I've stayed true to the paper, and if I've missed something, I highly suggest you study the paper a bit. It's a bit confusing in the start, but after a while it all starts making sense. The first thing that we need to do is actually calculate the initial values for the signal, for the noise, and for the thresholds. And this is how we do that, by finding the maximum peak in some area of the signal, for example in the first 5 seconds, and if there are no peaks, we just use the max of this, generally that signal in the first 5 seconds. When we've got all of those initial values, then we can actually start going through our algorithm. The code is pretty lengthy, especially because I also had to gather all of the variables for the plots, so to actually show you how this all looks. And I mean, if you want, you can find the code down below in the Element 14 community, and you can check it in more detail. But essentially, we're doing the logic that I've already explained in the drawing, where when we find a peak, we need to see whether it's higher than the threshold one or not. If it is, we can find a peak that's within the max delta in the filter signal as well. If that's the case, then we know that peak is the R peak, and we continue from there. Depending on whether it's first search, whether it's a search back, we update all of the values differently. Again, just following the paper, you can check it out for free online. And we update the RR1 and RR2 variables and arrays, as I've talked to you about previously as well. When we get through all of that, these are just some of the values that I wanted to print out, the initial ones, just to make sure everything is working. We can actually do some visualization and see how this looks like. So these are the final R peaks in the end on that segment, and this is how that looks like with all of the signal levels, noise levels, and thresholds. You can see as the peaks kind of drop here in the middle because of signal noise, electrode placement, stuff like that. You can also see that the signal level slightly drops here, but not enough. The algorithm is just adapting to the ever-changing signal, and that's why it's so good and can handle a lot of noise, as you can see in the pictures in the paper. And here is our filter signal, and as you can see here as well, all of the R peaks have been detected as they should. Of course, this is the ideal case, and whether this will work with a lot of noise when we run, that's something you'll find out at the end of this video. Before we get to the electronics and actually testing this device, we need to translate all of this Python code to C++. How I would usually do this would be just starting to write the Arduino code, starting to do tests, but this time I actually wanted to do something else and to try something new. That's why I tried using Cursor, and it actually turned out really good. What Cursor is essentially an AI agent, and how I used it is by using a few scripts that I know worked, like the sampling script you've seen before in the video, another script for uploading to the phone over BLE, and uploading here my full Pan-Tompkins algorithm that I've written in Python. I've instructed Cursor to actually take all of that and translate that into C++ into one unified script. It didn't work straight out. It needed a lot of polishing here and there, but in the end I actually finished up with pretty clean code that works rather nicely for what it is. So I was really happy with that, and also Cursor managed to adjust some stuff just based on context, like adjusting filters, stuff like that. So I'm really happy with how this turned out, and it actually saved me a lot of time not having to pretty much retype the whole code just in a different programming language. With the software complete, we can focus on the electronics and the mechanics of this project. Electronics will be rather simple, as you will see in the next clip. It will be just a couple of modules to connect everything together, and then I'm gonna show you the 3D model so you can print your own version at home. You can find all of the files available down on Element 14 community. As soon as we're done that, we can finally go for a run. Electronics for this project are really simple. My plan was not to be simple at all, and I designed that PCB, but again, that needs a redesign. So for this really DIY friendly version, we just need a few components. We need a Xiao ESP32 C3. We need the ECG module that you can find pretty much anywhere. We just need any kind of 1S LiPo battery, and we need a small boost converter to convert that 3.7 volts to 5 volts, and we let the ESP32 convert that 5 volts down to 3.3 volts that we need for our analog front end. Besides that, I just added a small switch to turn on or off the device, and added a small connector for charging. Let's take a look at the 3D model and then finally assemble it. Here's the 3D model of our device. So it's just a few 3D printed parts. This here is our main mount for all of the electronics. I'm just gonna use some hot glue to hold everything in place, including the battery, the small switch and the Xiao board. And down here we have some space for our button connectors and to thread a wire for our third electrode. Besides that, here's a small gasket that you can print either out of PLA or TPU. My idea was to make this completely waterproof, but one other idea I had for turning it on didn't work, so this switch just makes this not really that useful of a feature. And over all of that goes this cover, which you can either print in one color, or if you have a printer that can change colors, you can print it like this with the text. So this is how the whole device looks like. It's just a few 3D printed parts. You can use PLA or PTG or whatever else you want. So let's assemble it and finally go for a run. And our sensor is complete. As you can see, it has this pigtail with the third electrode, but it is what it is. I just had to add another button connector here, just to have any kind of contact with the body, and the signal was clean enough for the Pan-Tompkins algorithm to work, as you've seen in the previous clips. It turned out pretty okay. It's not too big, but we can make it much smaller by designing a custom PCB and using another IC that can work with just 2 electrodes. So the only thing left now is to go for a run and compare the results after that. Let's go. So finally time to go for a run. Let's go test this out. Prop running a tire here. I'll use this to record on Strava, and to compare that to, I'll use my smartwatch so we can compare the data later. Let's go for a run and I'll take you along. Okay, so checking in mid-run. Compared to my watch, which is at 131, as you can see, the heart rate is showing around 130. There are some oscillations, but we'll talk about that later in the video. Okay, checking in from the 4th kilometer.
So here's what I've noticed. When I'm keeping the pulse kind of steady for a extended period, they actually match up, the watch and the tracker that we made. But as soon as I try doing some major changes, this thing just can't keep up. The watch isn't that accurate either, but without proper data logging, we really can't know what the algorithm and how the signal looks like. So I'll try doing some literally pulse keeping using the watch, just keeping my pulse at a constant level and looking at the phone to see whether our tracker can keep that data. So 1.5 kilometers left. Let's finish that up and see how that data looks in the Google Collaboratory. So to about 120, 130, this thing is happy to keep up with the watch, but anything above that, it just falls short. And that's something that's definitely with the algorithm wrong, being too restrictive and not looking at new R peaks. So that's something we'll need to take a look at further. I'm gonna go and finish up this 5K and talk to you after that.
Now that I'm back from the run, it's time to analyze all of the data. If you look at these files here, I've downloaded them straight from my Strava account, and you can do that with any of your activities as well. And all you need is this library right here to actually analyze them in Python. So first we need to load all of the data. So this code will be available on Element 14 community if you wanna try analyzing some of your runs yourself. And first let's visualize the watch data. It's about as we expect. We can see the jump in pulse from 70 something to 150, which is to be expected from warm-up to actually running. That's about the pulse I run at. I know I'm not that fit. And I tried doing some harder sessions with pushing pulses around 170 or something like that, and also easier sessions just to see how the heart tracker performed at either of those sections. And in the end I had this long walk just to see whether that will suit our heart rate tracker more. If we take a look at that data, not really. If we take a look side by side, there is some resemblance, but not that much, as you can see on this graph here where we can see both of them. I was really happy in the beginning because if you take a look at the very beginning, they were really spot on one against each other, but then this 20 bit per minute gap just showed up and it didn't recover from there. There were some good segments like this segment right here where my pulse started to drop and it followed it rather nicely, but again, if we look at this segment here, there really doesn't look like to be much correlation here, and maybe it started looking a bit better again here. One of the mistakes was implementing that filter, which was too restrictive with the maximum change of 1 bit per minute per second, but that doesn't explain stuff like this. I've also implemented this part of the code if we want to check a certain part, certain time frame between these two. So let's check between 1951 and 1953, for example. That looks rather promising. Yeah, that's rather good because smartwatch does do a lot of averaging out. Also, the smartwatch had a lot of empty data points. I don't know why, but and it's not perfectly accurate. So getting a result like this is I'm actually really happy with it. And too bad we couldn't keep it all along the way. But yeah, this takes much more work, and the issue is to properly develop this. I need proper data logging to see whether we had some issue in the actual readings, whether this was just a pure algorithm problem. So this is something that I will do in the next version when I actually design the PCB properly, so we can actually make a suitable replacement for an off-the-shelf heart rate tracker for running. Thanks so much for watching the video. I'm really happy that we've gotten this far, though the results are still not that good. We've managed to record the heart signal, we managed to implement the Pan-Tompkins algorithm, but in the real world during the run it didn't work as we wanted, as you've seen from the data analysis clip. Is that to the signal noise? Is that to the algorithm? We really can't tell until we actually have some proper data logging. So my plan with this is to actually design a PCB with a different IC and add an SD card for data logging. If you have any other suggestions that you would like to see added to that PCB, leave them down below in the comment section on Element 14 community, where you can also find all of the files to download for free if you want to take a look at this project yourself. So until next time, see ya!